Thank you very much for that introduction and for the invitation to speak at this interesting workshop. In some ways, the work I do is very commutative and is very different from a lot of the things we've been hearing about so far. But as you'll see, there are some similar themes, kind of seeking both dynamic and static versions of Wasserstein metrics in generalized settings. So today I'm going to be speaking about some joint work that we're finishing right now with Nicholas Garcia-Trios from the University of Wisconsin and our own Georgia Nikolic, who's both a PhD student at UC Santa Barbara and has been one of the visiting grad fellows as part of this program. Okay, so my plan for today's talk is to begin by giving some motivation for why you might want a type of optimal transport distance on a space of vector-valued measures. And the two applications I'm going to give are going to come from, on one hand, image classification tasks, and on the other hand, gradient flows. So once we have these applications in hand, I'll discuss some of the previous works in this directions, both defining optimal transport distances on the spaces of vector-valued measures. And one particularly kind of inspirational work from us did this by leveraging previous work by Jan Maas and Ehrbar and many others on Wasserstein metric on graphs. So I'll also recall how previous work has studied Wasserstein metric in the graph setting. Once I have all of this groundwork laid, I'll go forward and I'll kind of define the new dynamic and static semi-metrics that we study. And our main result is a kind of a comparison of these metrics. So at first, we had hope that our dynamic characterization and our static characterization might coincide, and I'll kind of talk about why you might hope something like that would be true. In fact, they do not. And I can give an example of that. But the good news is that one always dominates the other. And furthermore, we're even able to show that they're topologically equivalent. So kind of I'll conclude with this main result, which relates these different type of dynamic and static optimal transport metrics. Okay, so like I said, I'll begin by giving a little bit of motivation. So here's just a fun, motivating problem to have in mind. So at the top here, we have images of clothing. These are images from a well-known toy data set called Fashion MNIST. And in this data set is kind of composed of these types of images of clothing, and each image has been labeled with the type of clothing. For example, sneaker, t-shirt, sandal, and so on. And it's well known that there are mild misclassifications in this kind of standard data set. For example, this has been labeled a coat. Probably most of us would guess it was a t-shirt, and then similar, this has been labeled a pullover or sweatshirt. Maybe this, again, looks more like a t-shirt. But we have this intuition that these misclassifications are somewhat mild. Like, it's not like this was labeled a sandal, So we have this intuition that there's a similarity in the space of labels. And so let's imagine that we have two labeled data sets. And I am going to assume that each of these data sets are comprised of images. Maybe they're the exact same images in both data sets, or maybe they're similar images or images that share some structure. And in each data set, the images have been assigned a label. And we're kind of imagining a situation in which the labels assigned by some mechanism over here might be slightly different than the mechanism used to assign labels on the right-hand side. But the labels themselves are the same. So t-shirt, trouser, pullover, dress, and so on. Okay, so we have these two labeled data sets. And the one motivating question might be, how different are these data sets? So to frame this question in terms of an optimal transport problem, I'm going to begin by representing each of the images as a point in a high-dimensional Euclidean space. So this image is one point, this image is another point, and so on. There's a lot of different ways to represent images as points in high-dimensional Euclidean space. Maybe since this is an optimal transport conference, I'll say that a particularly interesting one from the perspective of optimal transport is this linearized optimal transport framework developed by Wang, Slepchev, and co-authors. But okay, so there's many ways that we can represent these images as points in a high-dimensional Euclidean space. And we're going to assume that this space is endowed with a Euclidean norm so that the similarity between two images we see as kind of their closeness in this norm. So two images are very similar if their distance is small. And then similarly, we're also going to have a notion of, I'll call it dissimilarity between the labels. Okay, the reason I use this silly terminology is because I'm going to be thinking that Qij is large when the labels are very similar. So we have an intuition that pullover is very similar to coat. So the Qij between I pullover and J coat is going to be very large. I'm always going to be thinking about the case for simplicity that Qij is symmetric. So the similarity between pullover and coat is the same as between coat and pullover. And we think that kind of the Qij between those two is much larger than, for example, the number between pullover and sandal, because we have some intuition that those things are very different. Okay, so we would like to say that two data sets are similar if the images that they're comprised of and the labels assigned to those images are similar. So there's a variety of different contexts in which you might want to compare data sets in this way. So for example, perhaps you have two different classifiers. So you have two different ways of taking images and assigning labels to them, and you want to compare the performance of these classifiers. And we have an intuition that if the classifiers are essentially identical, and put the essentially identical labels with the images, except for the fact that one of the classifiers classifies a few coats as pullovers, somehow those are very similar classifiers. On the other hand, if one of them classified a few coats as sandals, okay, there might be a bigger structural difference between the two. Okay, so one reason you might want to do this is comparing the performance of classifiers. A second reason you might want to do this, this is kind of related to some previous work that I've done using optimal transport for jet tagging, is at the Large Hadron Collider. They have these two different experiments, the ATLAS and CMS experiment. And an important problem there is they get all of these images. You can really think of them as 2D images. Each image represents a jet, which is kind of a byproduct of the proton-proton collision, and they want to classify what type of jet it is. And so the ATLAS experiment has one mechanism by which they take their images and they classify the type of jet. The CMS experiment has a different setup, and one might want to compare the two. So here, in this case, both the images themselves and the labels assigned to them would be slightly different. Okay, so there's a variety of contexts in which you want to compare the structure of labeled data sets. How is this an optimal transport problem, or how does this represent, how does this relate to comparing vector-valued measures? So I'm going to represent the collection of images with a given label, I, as an empirical measure. So remember, so this is one point x1, that's another point x2, that's another point x3. And so if I looked at a weighted sum of Dirac masses, for now, let's just assume all of the weights mk are equal. So let's just say that mk is 1 over capital K. I'll talk a little bit more about the weights in a second. But for now, we can think that for each collection of images corresponding to a single label, I can construct an empirical measure of all of those images. And so in this way, each of my labeled data sets can be represented as a vector-valued measure, which one measure for each of the labels. And then now I want a notion of distance on the space of these vector-valued measures so that if the data sets are similar, they're close in this distance. Okay, so this is one motivation where you might want to define a notion of distance on the space of vector-valued measures. Because the theme of this workshop is about dynamics, let me mention a second motivation, which could come from gradient flows. I'm actually going to start off a little bit on the optimization side. I'll say more in a second, more at the end about that. But let's assume you want to solve this kind of problem. You have a target measure, which is a vector-valued measure, mu bold. So I'll be using bold to represent vector-valued measures within components. And let's assume we have some sort of loss functional that in some sense tells us kind of how similar or different two vector-value measures are. And then we have a constraint set C. So a common problem that you want to solve across the sciences is you want to minimize this notion of loss function subject to that constraint set, or find the row in that constraint set is similar to mu in the sense L. So for example, in sampling, your constraint set C might be the constraint set that rho is only comprised of empirical measures. And then you have a given vector value measure bold mu, which is not an empirical measure. So you try to find the empirical measure that most closely approximates mu. So a natural way to do this is by a gradient descent, but I think as probably everyone in this room appreciates, when you start talking about gradient descent of an objective functional, you need to say which kind of gradient. And so if you have a notion of distance on the space of vector valued measures, you can, for any notion of distance, you can start at least talking about gradient descent, for example, in discrete time with this type of minimizing movement scheme, or well known as the Jordan-Kindler auto scheme, when d is the 2 Wasserstein distance. And on one hand, just by going down gradient descent, with respect to some metric, you're not guaranteed that you're going to go to a minimizer. You would need some kind of convexity properties of your energy functional with respect to your distance in order to ensure that. But even if you don't have any hope of always going to a minimizer, even if you're just going to be flowing to an approximate minimizer or a critical point, if you pick a good notion of distance, something that following the gradient descent will give you is it'll always give you reasonable stability properties with respect to perturbations in that distance. Okay, so this also motivates the need for defining a good notion of distance on the space of vector valued measures that incorporates our intuition that a perturbation between coat and pullover is not a bad problem, but a perturbation between coat and sandal is a big perturbation. Okay, so motivated by both of these applications, today I'm going to kind of talk about different answers to the question of what is an appropriate notion of distance between vector valued measures. So let me tell you the specific class of vector valued measures that I'm going to be focusing on. So we'll suppose that we have omega as a subset of RD that's closed, and we have an in-node graph G. This is going to represent the different labels like coat, sandal, sneaker, and so on. And we're going to consider this class of measures. I was told that there are a lot of little buttons on here, and if I pressed the wrong one, exciting things would happen, and sure enough. So this is the class of vector valued measures that we're considering. So it's measures within components. Each component is a finite Borel measure on omega. And the important hypothesis that I'm going to make is that if I look at the sum of all of the components, this also gives me a finite Borel measure, and I'm going to assume it's a probability measure on omega. So this is like a normalization hypothesis. I'll say more about this in a second. This quantity, the sum of all of the components of the measures, is going to be such an important quantity in today's talk that I'm going to give it a name. I'm going to call it mu bar. So this is a probability measure. Let's think about a specific example, and kind of going back to the classical 2 Wasserstein case where we imagine we're moving around piles of dirt. Let's again imagine we're moving around piles of dirt, but now we have 3 different types of dirt. We have blue dirt, red dirt, and yellow dirt. This hypothesis here is just saying that if I look at the distribution of the total amount of dirt of any color, it has to have total mass 1. Okay, so let me see this. Okay, so in fact, there's been several previous works looking at different types of optimal transport distances on exactly this class of vector valued measures. One work that was particularly influential for us was this work by Chen, Giorgio, and Tannenbaum, which defined a type of dynamic distance on this space, a type of dynamic 2 Wasserstein metric, by taking a product space structure between Wasserstein metric on the graph in the classical 2 Wasserstein space. Subsequent work by Bacon defined a type of static distance on this space via Kantorovich formulation. So here he looked at kind of collections of transport plans which told you how to move mass from the ith component of the measure mu I to the jth component of the measure nu. And he even allowed for the cost functions of moving mass between these different components to depend on which components you were moving between, and studied kind of duality of this Kantorovich formulation and what compatibility conditions you needed on the cost to ensure that this was truly a metric on this space of vector-valued measures. And then also, there's been a lot of work on sort of one Wasserstein type metrics, or metrics that are kind of dual to bounded Lipschitz distances by kind of both Tedeschi, Metvier, and Mirabeau, and also here at UCLA, Ryu, Chen, Lee, and Osher. But our goal was really to focus on the W2 setting. So our work is much more closely related to these first two works. And our goal was to find a W2 type distance that united these dynamic and static perspectives. And we wanted one that had both sort of a formal Riemannian structure to admit the study of gradient flows, and also in image classification tasks, this formal Riemannian structure has also been used to develop kind of formal linearizations of the two Wasserstein metric, which have really good behavior in image classification tasks and are much less numerically expensive. Okay, so this was our goal. And so since I said this work was particularly inspirational for us because it kind of combined this product space structure on the graph and the classical two Wasserstein case, let me also tell you a little bit about Wasserstein metric on the graph. This idea that I'm going to present was originally introduced by Jan Maas. I'm going to maybe use slightly different terminology than he did, but you'll see it's the same. So I'm going to assume that I have a graph within nodes. And before I just told you that each node represented each label. Now I'm going to tell you that it's a weighted graph where the weight of the edge connecting node I to node j is this number qij. So this represents the similarity of these two nodes. So this is a large number if they're very similar, and a small number, or even 0 if they're completely different. If we want to write down what is the space of probability measures on the graph, a probability measure on the graph can just be expressed as a weighted sum of Dirac masses at each of the nodes, where my weights are always non-negative and sum to 1. So there's this one-to-one correspondence between probability measures on the graph and these vectors in Rn pi, which represent the weight of each Dirac mass. Here is a cartoon of what's going on. So here I imagine I have a 3-node graph. Here the edge weights are 1, so we're imagining that blue is related to red and blue is related to yellow, but this edge weight is 0, so red and yellow are not related. And I'm looking at a probability measure that has mass 0.5 there, 0.25 there, and 0.25 there. And Maas's Wasserstein metric was a kind of dynamic formulation of the Wasserstein metric, inspired by the classical result of Benamou and Brenier, where Maas looked at all solutions of the graph continuity equation to flow between p at time 0 and p tilde at time 1, and sought one that minimized this notion of action. So there's some symbols here that I need to define. So first, I'm going to say what I mean by p check. So the graph divergence operator, this is something that takes in matrices and spits out vectors. So I need a notion of flux that's matrix valued or defined on the edges of the graph. And so on one hand, my velocity is sort of naturally matrix valued. This is sort of saying how mass is flowing from the ith node to the jth node. But my density is not naturally matrix valued, it's naturally vector valued. So I need some sort of interpolation function in order to take the average of the amount of mass at node I and the amount of mass at node j and give me a kind of matrix valued interpolated density. And so this represents kind of the flux in my continuity equation. And there's various choices of interpolation function theta that you could have in mind. For example, just an arithmetic average, a geometric average, a logarithmic average. We consider even more general hypotheses on theta. And all of the results I'm going to talk about today apply to all three of these, with the exception of, I'm going to give some examples at the end which only apply to interpolation functions that vanish at the boundary, such as these two. Okay, so Moss introduced this type of...
just
yes?
correct. In the divergence, you also have the weights, right?
Say it one more time.
In the divergence, you have the weights.
Thank you, yes. So in this, this graph divergence includes the weights of the graph. And I'm actually going to take that out on the next slide to clarify things a little bit. Okay, but before I get there, let me just kind of continue summarizing some of these existing results. So if it is a connected graph, meaning that there is a path between any two nodes with positive weights, so that every node is at least positively related to every other node along some path on the graph. Moss showed that if you look at the collection of strictly positive probability measures on the graph, and endow it with this notion of distance, it turns out to be a smooth Riemannian manifold. And so on one hand, this seems like a very nice space. But on the other hand, as Wilfred showed us, this is not a very nice space. There's a really interesting result due to Gangbo, Li, and Mu. Well, first of all, the manifold is not complete. Here I was just talking about the collection of strictly positive measures. But it can be even a little bit weirder. They gave an interesting example where you can take 2 points in the interior of the measure, of the manifold, in other words, two strictly positive probability measures. And if you look at the geodesic between them, it touches the boundary. Okay, so this could make you a little worried about this space and kind of maybe suggest that sort of branching of geodesics is possible. To get back to the previous question, let me rewrite Jan's Wasserstein metric on the graph in a slightly different setting where I take the weights out of the continuity equation because they are sort of hidden in the graph divergence operator. For simplicity, I'm just going to assume that all of the weights are positive, though, okay, could be very small if they're really not related. So now I'm going to rewrite the graph continuity equation. So now it's just the divergence operator on a complete graph where all of the nodes edges have weight 1. So I've kind of taken these QIJs out of the graph divergence operator, and then they sort of appear in this way in the action. Why I like writing it in this way is because now you can really see the effect of the QIJ on the minimizing curve. Basically what I'm trying to do is I'm trying to flow from P to P tilde according to this graph continuity equation. And we can see that if two nodes are very closely related, so that QIJ is very large, the penalty given to a velocity along connecting those two nodes is very small. On the other hand, if two nodes are really unrelated, so that Q is very small, you have a huge penalty to flow between them. So it's symmetric. So my QIJ is symmetric. So I think a lot could be said in the detailed balance case, which is a more general hypothesis than the symmetric case. But because our inspiration was from these sort of similarity graphs, we began in the case where it was symmetric. Okay, all right, so this is just kind of recalling the existing work in the graph of Wasserstein case. A perspective that was very useful for us, also was used in this previous work by Gangbo, Li, and Mu, is that you can think of probability, there's a one-to-one correspondence between probability measures on the graph and points in the simplex. So let me just, I drew some beautiful illustrations over here to show this idea. Okay, so let's imagine that I have a two-node graph. So if I have a two-node graph, the simplex I'm interested in is just the interval, or the simplex in one dimension, between 0 and 1. And so if I have a probability measure that maybe gives me, let's say, a little bit of mass that's at the red node and a lot of mass at the blue node, maybe we'll say it's 0.75 at the blue node and 0.25 at the red node, we can represent this probability measure as just a point on the line at location 0.75. Okay, so basically just the point in the interval tells you how much mass to put at the blue node, and then you know how much mass to put at the red node because it has to be a probability measure. If you have a 3-node graph, it's the same story. If I know how much mass has to be at the blue node and at the red node, then I know what the first 2 coordinates should be. So maybe it's 0.5 for blue, and maybe it's only 0.25 for red. And then once you've prescribed both of those, you know how much should be yellow. Okay, so this is just to say that you can think of probability measures on the graph, which maybe at first glance feel like a very discrete object. They're really very kind of continuum objects. They're just points in the simplex. Okay. All right, so because there's this one-to-one correspondence between probability measures on the graph and points in the simplex, okay, I drew the same picture. We can have like this one-to-one correspondence between them, and we can take the same geometry that Moss put on the graph and imagine that geometry on the simplex. So here's an illustration of this interesting counterexample due to Gangbo, Li, and Mu, where you can take 2 probability measures in the interior of the simplex and find a geodesic connecting them that hits the boundary. Okay, so sometimes it's nice to visualize things in terms of the simplex. Another nice thing is that even when you endow this simplex with this kind of somewhat weird graph of Wasserstein metric, it turns out that it's still topologically equivalent to the simplex with the usual metric. And then again, of course, on the interior, it's a smooth Riemannian manifold. Okay, so now that I've laid out some of the previous work, let me talk about the variance of these metrics that we considered and how we were able to relate them. To begin, to define a dynamic metric on the space of vector-valued measures, we want to follow this Benamou-Brunier framework and begin by prescribing what is a continuity equation on the space of vector-valued measures. So now I'm going to be assuming my spatial domain is some closed convex domain. I have my connected weighted graph. And then my continuity equation is as follows. So this probably looks a little weird, so let me tell you what it is. So I have velocities, ut. So they depend both on space and time, x and t. They're vector valued. There's n components. Each one of these components describes the spatial velocity of the ith component of my vector valued measure. And then I have these other velocities, v of t. These are matrix valued, and these describe the velocity in the graph space, or the rate at which blue mass mutates into yellow mass. So to say a little bit about, okay, so I wrote the continuity equation in a very, very concise form. What I mean here, this is just component-wise multiplication of my measure and my velocity. This is just component-wise divergence. And then this check still means the exact same thing as before. So this is still my flux on the graph. Now at this point, you might object a little bit because this rho I and rho j, these are just supposed to be finite Borel measures. And I told you that one of the thetas I was interested in was the geometric mean, where I'd have to multiply rho I and rho j and then take the square root. So maybe multiplying measures is maybe a little weird. This is in fact just an abbreviation for the following quantity. So I imagine I take the Radon-Nikodym derivative of each component with respect to the sum of all of the components. And because my averaging operator theta is always one homogeneous, this is morally speaking that. Okay, so just take this as an abbreviation for that measure throughout my talk. Okay, so I have a notion of a graph continuity equation. Let me also write it in like a slightly simple case. So if the velocity field on the edges of the graph is symmetric, this all simplifies, and we can see that the ith component of my vector valued measure satisfies the following equation. So this looks like something much more similar to the classical 2 Wasserstein setting. It's at the ith component of rho. We have kind of, this is the usual continuity equation that describes its transport in physical space. And then we also have a reaction term, which describes how it kind of yellow mass mutates into blue mass. Okay, and I'm going to let C rho tilde denote the solutions of this vector-valued continuity equation that start at rho and end up at time 1 at rho tilde. So given a solution to the continuity equation, now we just need to prescribe a notion of action to get a dynamic metric. So here's the action that we consider. Basically, it's just a sum of the action in physical space, and then also an integral of the action that Moss considered on the graph. This leads to a dynamic distance. We look at all solutions of a continuity equation flowing from one vector-valued measure to another, and we seek the one that has minimal action. And this turns out to be kind of a reasonably nice definition. We can show that this is indeed a metric on this space of vector-valued measures with finite second moment. And furthermore, that the infimum is attained so that a minimizer exists. Okay, so how does this compare to the dynamic metric introduced by Chen, Georgiou, and Tannenbaum? So it turns out the continuity equation we consider is exactly the same, with one key difference. Whereas the interpolation operator that we look at is inspired by this original work by Moss. Chen, Georgiou, and Tannenbaum look at a different interpolation operator, which is like an upwinding interpolation operator. So in this sense, it's basically saying if the velocity is going from node I to node j, the density you should be looking at is the amount of mass at node I, and then similarly for the other direction. And then this difference kind of propagates. So in the action, the spatial terms of our action are the same as this previous work, but the kind of graph terms in the action, ours sort of follows the Moss framework, and theirs kind of is the natural choice given this upwinding interpolation. But kind of why didn't we follow the same scheme? So as observed in the original work by Chen, Georgiou, and Tannenbaum, and then kind of further even developed in work by Esposito, Patachini, Schlichting, and Slepchev, is that the kind of corresponding sort of distance you would get from this Benamou-Brenier type formulation is not symmetric. So somehow the effort of flowing from mu to nu is not the same as effort from flowing from nu to mu. And it leads to, instead of a Riemannian structure, maybe a type of Finslerian structure. So because it was essential in our work, our goal was sort of uniting dynamic and static. And a key piece of that is leveraging the Riemannian structure of the simplex, because we use this result due to Licini characterizing absolutely continuous curves in the simplex in terms of continuity equations. So this was really essential to our approach. And so we needed to work in this kind of nice Riemannian setting developed by Moss. Okay, so now I've told you a little bit about the dynamic metric. And then, maybe with the surfeit of optimism, we sought a static metric, which was equal. And maybe we were so optimistic because we hoped there could be an analogy between our distance and the Hellinger-Kantorovich distance. And so just to recall a bit the Hellinger-Kantorovich distance and tell you why we hoped for this analogy. The Hellinger-Kantorovich distance, this is a distance not between probability measures, mu and nu, but between finite Borel measures. So they can have unequal mass. And it again has a dynamic formulation so that the square Hellinger-Kantorovich distance is you look at all ways of flowing from mu to nu according to this continuity equation with a reaction term. And you seek the one that minimizes this notion of action that kind of penalizes transport in physical space and penalizes reaction. And there's this beautiful result due to Liero, Mielke, and Savary that observed that any finite Borel measure, mu or nu, we can think of as a projection of a probability measure. So with mass 1 on the cone space, Okay, here's the formula for the projection. This is not so important. And furthermore, that the Hellinger-Kantorovich distance between any two finite Borel measures is the same as saying, look at all different ways, all different probability measures on the cone space that project down to mu and nu, and do the regular Wasserstein distance between them with the ground metric coming from the cone space. And so this was a very appealing type of static metric for us, because this is, again, just like an infinite dimensional linear program with linear equality constraints. And so you might ask, why the cone space? Where's the cone? Why does that come into play? Let me just draw a little cartoon. So I imagine that I have a finite Borel measure on the real line, and I'm going to think of this as a probability measure on the cone. For simplicity, let's just imagine I have periodic boundary conditions here, so this will make it look more like a cone. And what I do is I introduce a new dimension, r. So my location in physical space tells me how far I am around the cone, and then where I am in this r dimension tells me kind of how much mass there is. And so so we identify the point where r equals 0 and x has any value. We consider all of those the same point. And any finite Borel measure can be expressed as a probability measure on the cone, where kind of how far up or down it is on the cone tells you how much mass to put at that point. Okay, so we had this previous result, and we were wondering if we could do something similar. Oh, I got my animations out of order. Okay, so motivated by this, we considered a similar projection operator. I think going through the formula is probably less valuable. Okay, this is the formula for I equals 1 to n minus 1. That's the formula for n. But let me begin actually with a picture. Okay, so here is the vector valued measure we have in mind that tells us the distribution of blue, red, and yellow dirt. And so now we're going to think of this vector valued measure as a probability measure on the lifted space. So since we're thinking of 3 colors right now, our simplex is just the triangle. And we're going to look at the product of the triangle with the real line, because in this case, omega is just the real line. So what I've tried to draw here with this sort of prism is the product of the triangle with the real line. And I want to represent this vector valued measure as a probability measure on this. It's kind of like a giant Toblerone bar. So I want as a probability measure on this. Okay, so of course there's a variety of ways to do it, but this is the specific way we have in mind. So that probability measures here on here project down to here. And so how I'm going to do it is I'm going to say, well, I've got 100% blue mass at this location. So in my canonical lifting, I'm going to take each component of my vector valued measure, and I'm going to lift it to a measure on the Toblerone bar by putting all of the mass of a single component along the edge of the simplex corresponding to that color. So all of the blue mass is going to be distributed on this edge, which somehow represents 100% blue color. We've tried to shade it so it's lighter at the boundaries and darker in the middle to evoke that it's sort of like peaked in this way. So this is a measure concentrated on that edge. The red mass gets lifted here, and then the yellow mass is sort of what's left over and is lifted here. Okay, so this is the canonical lifting. So given any vector valued measure, you can always represent it as a probability measure on the lifted space in this way by lifting to the edges. But of course, there's many other ways of doing it. Like for example, I've tried to draw that the yellow triangle and the red triangle are at the same location in physical space. They're just different colors. And so whereas here, the yellow and red triangle were represented as sort of 100% yellow mass and 100% red mass, but at the same location in physical space, here you could also represent it as 50% red, 50% yellow, but with twice the amount of mass, so kind of like halfway down the bottom of the prism. Okay, so there's a variety of ways to represent vector valued measures as probability measures on this lifted space. And we had a hope that if we defined a type of static distance, basically by looking at all of the different ways of representing these vector valued measures on the lifted space, and considering just the Wasserstein, regular Wasserstein distance between them. Of course, here the ground metric on our simplex comes from the graph geometry. It's this funny metric. Yeah?
But before, for Milke, Leroy, and Savare, the distance was not, it was the classical distance on the cone, or there was some, right?
It's just it's the cone distance coming.
It was a Wasserstein distance with the distance on the cone.
With the ground distance is the cone distance, exactly, yeah. Okay, so we kind of hoped that this analogy would work. And now, of course, there's another type of metric you could consider, which is just look at the canonical liftings, not the infimum over all possible liftings, but just these two where you lift to the boundary and say maybe that's a notion of static distance. And so to start with the bad news, it turns out that this is not a metric, this first idea that we had. It's only a semi-metric because it fails the triangle inequality. Of course, this second thing is a metric because there always is such a canonical lifting, and so the fact that it's a metric just follows from the same properties of the regular two-Wasserstein metric. And then, of course, by the way we've defined them, we know that this metric in terms of the canonical lifting always dominates the first metric.
So why? It doesn't have the triangular inequality, you said?
Yes, the first one fails the triangle inequality.
Even though it's a nymph of distances, I'm confused. So if I have three states and I take couples and I'm confused about, maybe I'm missing why it doesn't satisfy it. So if I have mu, nu, and sigma, and I take lambda 1 and lambda 2, lambda 3 optimal for the other two, and I take lambda 1, lambda 3, doesn't...
Well, the problem is the infimum. So I'll give you an example. Okay. And furthermore, I guess, so on one hand, this is the distance we were most interested in to begin with because of this course, analogy with Hellinger-Kantorovich. But this distance turned also out to be kind of interesting in of itself. It turns out that you can frame this also in a Kantorovich formulation, just like that studied, for example, by Bacon. So you can write this in terms of the transport plans of moving mass from the ith component to the jth component in a certain type of cost function. Okay, so now how do all of these different things fit together? So you already know that our candidate for our static metric that coincided with our dynamic cannot coincide because it fails the triangle inequality. But how do they relate? And so our main result is that while they're not the same, they can be ordered. So it turns out that our dynamic distance is always less than or equal to this static semi-metric, is always, of course, less than or equal to the metric in terms of the canonical liftings. And we can show examples of equality and inequality in all of these cases. So this made us a little sad at first. We were really hoping for some sort of equality here. But the good news is that it turns out that all three of these things can be bounded from below by just the usual bounded Lipschitz distance between the vector valued measures, of course, up to a constant depending on the edge weights. And if we're on a bounded domain, they can be bounded from above by a square root of a bounded Lipschitz distance. So this at least tells us that we can rescue some sort of topological equivalence of the three. Yes?
Sorry, I'm just catching up on the previous slide.
Yes.
So the lambdas that you defined, right?
Yes.
For any given mu, there was a lambda mu, or
say it again.
You were showing.
Yes. So exactly. So the lambda mu. I went too far back. The lambda mu is this canonical lifting, and so. This is a.
I just meant the Toblerone bar.
Yeah, exactly. The Toblerone bar. That's what it's all about. So, so for any mu, I can define a canonical way of representing it as a probability measure on the Toblerone bar by just taking each component of the vector value measure and representing it as a distribution on the edges of the lifted space. So this is good because now we know for any vector valued measure, there's at least one way of representing it as a probability measure on the simplex. in general, there's a lot of ways as representing it as a probability measure on the simplex. And so that's why, in general, this first static metric we were interested in, taking the infimum over all possible ways of doing it, might be a bit different from just looking at the Wasserstein distance between the canonical liftings.
It's not necessarily clear that for mu, the canonical one is the one that you should be looking at, right?
Right, exactly. So yes, yes. Mm-hmm. Yeah. Okay, so at least we're able to kind of rescue a bit of topological equivalence. In the last 5 minutes, let me just give a bit this example for why this example. The way I'm going to explain it right now is that why this static distance is strictly larger than the dynamic distance, but it's actually the same example. You'll be able to see this is why the triangle inequality fails. Okay, so I have a vector valued measure. We're imagining that it's a Dirac mass of blue dirt at location A and a Dirac mass of red dirt at location negative A. And they're equally weighted, 1/2, 1/2, so that the total mass is 1. And so I'm going to use dots to indicate this measure. And then I have another vector valued measure, nu. In this case, all of the mass is concentrated at the origin. And I have B, blue mass, and 1 minus B, red mass. And I'm assuming that B is strictly greater than 1/2, so more blue than red. And so I'm going to represent this measure nu with a solid line. And so if we wanted to bound from above the distance between mu and nu in terms of the dynamic distance, we have to say, how can we evolve between them, allowing ourselves to both mutate the color and transport in physical space. And you can show that one admissible path between them is first I just decrease the amount of blue dirt to 1/2 and increase the amount of red dirt to 1/2, and then I transport them to the right and left. So this is one admissible path. So you can write down as a solution of this vector value continuity equation. And the action or the effort required by that path is just A, that's the effort it takes to move them in physical space, and this distance. So here it's the distance on the simplex, which has been endowed with this kind of weird graph Wasserstein distance. So it's topologically equivalent to the usual Euclidean metric, but not exactly the same. If theta is the arithmetic interpolation function, then this is the same. Then this is exactly just b minus 1/2. But for other thetas, it's different. So we can kind of estimate the dynamic distance, bound it from above in this way. On the other hand, what's going on with the static distance? So for the static distance, there's only one way to represent this vector valued measure as a probability measure on the lifted space, and it's the canonical lifting. And that's because I basically just have to say all of the mass at location A is 100% blue, and so I put a Dirac mass at 1, and all of the mass at location negative A is 0% blue, in other words, red. So I have to put a Dirac mass there. So there's only one way to represent it. And on the other hand, there's choices. There's multiple ways to represent the nu. I'm going to represent it as sum of these two Dirac masses. And we can see that if we kind of averaged these two locations, we would see the average of 1 and 2b minus 1 is b. And that reflects the fact that the percentage, that all of the dirt at the origin is b% blue. Or there's a b amount blue. Okay, so this turns out to be the best way to lift it in terms of the semi-metric. Then when I look at the Wasserstein distance on the lifted space, it just wants to move the Diracs in that way. And so I can show that according to my semi-metric d, the distance between mu and nu is this. In the case when I choose theta to be not the arithmetic interpolation, so that this is not just the usual Euclidean distance, I can show that there exist numbers A and B so that the left is strictly smaller than the right. And basically the idea is that If theta is, for example, a geometric averaging instead of an arithmetic average, it's a lot more effort to move things once you get close to the boundary than in the interior. So here you're just moving it between b and 1/2, and here you're having to move it from 2b minus 1 all the way down to 0. Okay, so that's the problem. And maybe sort of intuitively, like if we were going to try to recreate what was going on in the dynamic perspective in the static space, we would want to start off with the Dirac mass here, move it up there, split it, and then move it to the right or left. We would want that to be our geodesic in the lifted space, but you can't kind of split things in this way. This is not like an admissible geodesic. So that's sort of intuitively what's going wrong. Okay, so with all of this in mind, a natural question to ask would be, well, which metric should you use? And so I think the dynamic metric, this is the one that's more naturally lends itself to gradient flows. Like for example, if I went back to that, the motivation from the beginning, I was looking at some sort of loss function between vector valued measures. Maybe I just consider the sum of the KL divergence between all of their components, and I look at its gradient flow with respect to our dynamic metric, I would get this system of PDEs. So we see the familiar Fokker-Planck equation, and then we see kind of this sort of reaction term, which describes the mutation between the different components. And then on the other hand, I think the static metric to me is particularly interesting from the perspective of kind of classifying classifying these different types of data sets, talking about the similarity of them, especially in the case where you might have a large number of data sets. Even though we sort of lack the formal Riemannian structure for our static metrics, still some things can possibly be said about linearization, with the caveat that this simplex has a really weird geometry and could potentially have branching of geodesics. So I think something that I really enjoyed about this project is that I really have never wondered about the existence of a Monge map on spaces with branching geodesics until this. And so this was sort of a fun project that, it took me into this weird geometric setting. So thank you very much.